In July of 2022, NASA released 5 images, just 5. And within 48 hours, the entire scientific internet went quiet in a way that had nothing to do with disappointment. Astronomers who had spent their entire careers preparing careful, measured, professional responses to new data were posting things like, "I am not okay," on social media. One astrophysicist at the European Space Agency reportedly walked out of her office, sat down on a bench outside, and just stared at the sky for 20 minutes. That is not a metaphor. That is what happened. And when you understand what those images actually contain, what they are really showing us beneath the surface of the pretty colors and the glowing clouds of gas, you will understand exactly why. Why Webb sees what no telescope before it could. Here is something that most coverage of the James Webb Space Telescope gets completely wrong, or at least severely undersells. Webb is not just a better Hubble. Calling Webb an upgraded Hubble is like calling a submarine an upgraded rowboat. They are both vessels that deal with water technically, but the comparison collapses immediately under any real scrutiny. Hubble, launched in 1990, sees the universe primarily in visible light, the same narrow band of the electromagnetic spectrum that your eyes can detect. It also sees some ultraviolet and some near-infrared, and it did this magnificently. Hubble gave us some of the most important images in the history of science. Nobody is taking that away from it. But here's the problem with visible light. The universe, it turns out, hides most of its secrets behind it. When stars are born, they are born inside dense clouds of gas and dust. That dust absorbs visible light completely. You point Hubble at a stellar nursery and you see a wall. A beautiful, dramatic wall of cloud. Yes, but a wall nonetheless. Whatever is happening inside, the actual birth of stars, the jets of material exploding outward, the formation of what might become solar systems, all of it completely invisible to visible light telescopes. Infrared light, the kind Webb is specifically engineered to detect, passes through that dust like it is not there. Webb's primary mirror is 6.5 meters across. For reference, Hubble's mirror is 2.4 meters. But the size is almost a secondary consideration. The real engineering achievement is the temperature. To detect the faint infrared glow of objects billions of light years away, the telescope itself has to be colder than the signal it is trying to detect. Webb operates at negative 266 degrees Celsius. That is approximately 7 degrees above absolute zero. The coldest possible temperature in the universe is absolute zero. Webb runs 7 degrees above that. They achieved this by deploying a sun shield the size of a tennis court, a 5-layer membrane of Kapton that blocks heat from the sun, earth, and moon simultaneously. The hot side of that shield faces temperatures of around 85 degrees Celsius. The cold side, where the instruments live, sits at negative 233 degrees Celsius. On the same object, separated by 5 thin layers of material, the gold coating on Webb's 18 hexagonal mirror segments is not decorative, by the way. Gold reflects infrared light better than any other material. Each of those 18 segments had to be aligned to within 1/50,000th the width of a human hair to function as a single mirror. That alignment was performed remotely, 1.5 million kilometers from Earth, by engineers using actuators the size of your thumbnail. I want you to sit with that for a moment. 1.5 million kilometers away, aligned to within a fraction of a human hair, working correctly on the first try. The fact that this telescope exists and functions at all is genuinely one of the most extraordinary things our species has ever done. And that is before we get to what it found, the cosmic cliffs, and what it actually shows. The first image most people think of when they think of Webb's early releases is the one that looks like a mountain range at sunset. Towering peaks of rust and orange and gold, with a sky above them alive with stars and light. It looks like a painting. It looks like someone's concept art for a science fiction novel. It looks, honestly, like something a very talented and slightly dramatic art student would submit for their final project. It is called the Cosmic Cliffs, and it is a region at the edge of a star-forming nebula called NGC 3324, located in the Carina Nebula, roughly 7,600 light-years from Earth. Here is what you are actually looking at when you see that image. Those cliffs are not mountains. They are the edge of a giant gaseous cavity being carved out by the ultraviolet radiation and stellar winds from extremely young, extremely massive stars located just above the frame. The tallest of those peaks extends approximately 7 light-years high. 7 light-years. Our entire solar system, from the sun to the outermost edge of the Oort cloud, is roughly 2 light-years across. These cliffs are 3.5 times taller than our entire solar system is wide. But that is not what made astronomers go quiet. What made them go quiet were the jets. Scattered across the image, if you know what you are looking for, are dozens of previously unknown features that Webb revealed for the first time. Bright streaks and knots of material, some just a few pixels wide in the original image, that turned out to be jets of gas, and material being blasted outward by newly forming stars still embedded inside the cloud. These are protostars, stars in the process of being born, that we had no idea were there because they are completely hidden behind the dust, invisible to Hubble, invisible to every telescope that preceded Webb. In a single image, Webb revealed an entire hidden population of infant stars that our previous instruments simply could not detect. And here is the detail that the press release is kind of buried, probably because it is slightly mind-bending to explain. The region shown in the cosmic cliffs image is only a small portion of NGC 3324, a tiny crop of a much larger structure. Webb was not even pointing at the most interesting part of the Carina Nebula. This was essentially a test image, a warm-up. Let us see if the telescope is calibrated correctly image. That was the warm-up. I genuinely do not know whether to find that inspiring or slightly terrifying. I am going to go with both. Stephan's quintet, 5 galaxies and a shock wave moving at speed that breaks your brain now. Stephan's quintet. If the cosmic cliffs image is the one that makes people say that cannot be real, Stephan's quintet is the one that makes physicists get very quiet and start doing math on napkins. Stephan's quintet is a group of 5 galaxies located approximately 290 million light-years away in the constellation Pegasus. It was discovered by French astronomer Edouard Stephan in 1877, which means for nearly 150 years, we have known these galaxies were there, seen them interact, studied their dynamics. We thought we understood them reasonably well. Webb's image of Stephan's quintet is the largest image Webb released in that first batch. It covers an area of sky equal to about 1/5 the diameter of the full moon. And within that image, there are over 150 million pixels of data showing interactions between these galaxies at a level of detail that simply did not exist before. 4 of the 5 galaxies in the group are genuinely interacting, gravitationally entangled with each other in a slow-motion cosmic collision that has been unfolding over hundreds of millions of years. The 5th galaxy, NGC 7318a, is actually a foreground galaxy, much closer to us, only about 40 million light-years away. It just happens to appear in the same region of sky, a cosmic photobomb that fooled astronomers for decades. Webb's data confirms this conclusively. Bit awkward for NGC 7318a, honestly, but here is what the Webb image revealed that changed things. Between 2 of the colliding galaxies, there is a shock wave, a bow shock created as one galaxy plows through the intergalactic gas of the group at speeds of around 800 kilometers per second. That is roughly 2,880,000 kilometers per hour. For reference, the New Horizons spacecraft the fastest object humanity has ever launched, travels at approximately 58,000 kilometers per hour. The galaxy is moving approximately 50 times faster than our fastest spacecraft. And this shockwave heats the intergalactic gas to tens of millions of degrees, causing it to glow in X-ray light. But Webb, because it sees in infrared, can see what happens in the turbulent gas after the shock, where hydrogen molecules are being heated and excited, creating specific infrared signatures that tell astronomers exactly what the gas is doing at a molecular level. Here is the thing that genuinely breaks your brain about this image, though. Because it is a group of galaxies at different distances, you are simultaneously looking at 3 different moments in cosmic history in a single photograph. The foreground galaxy is showing you what it looked like 40 million years ago. The interacting group is showing you what they looked like 290 million years ago. And the background galaxies, the tiny smudges behind everything, some of them are showing you light that is billions of years old, a single image, multiple epochs of cosmic time simultaneously. Photography has never done anything like this before. It may be the single most temporally complex image ever captured by any instrument humans have ever built. The deep field, the most important photograph ever taken. I am going to make a claim here, and I am going to stand behind it. The Webb Deep Field image of SMACS 0723 is the most important photograph ever taken by a human being or a machine built by human beings. Not the most beautiful, not the most technically impressive, though it is both of those things. The most important. Here is why. When NASA released this image in a presentation by President Biden on July 11th, 2022, the night before the official science release, the description given was that it showed thousands of galaxies in a patch of sky, roughly the size of a grain of sand held at arm's length. Let me restate that. If you hold a grain of sand between your fingers and extend your arm and look at the tiny sliver of sky behind it, what Webb captured in that space contains thousands of entire galaxies, each galaxy containing hundreds of billions of stars, each star potentially hosting planets in the space behind a grain of sand. But the image contains multiple layers of revelation that popular coverage consistently fails to fully explain. First, there is the gravitational lensing. The massive galaxy cluster in the foreground, SMACS 0723 itself, is so heavy that it bends the fabric of space-time around it. This bending acts like a natural lens, magnifying and distorting the light from objects behind the cluster. Those curved, stretched arcs of light you see in the image, the ones that look like someone smeared the galaxies sideways, those are not imaging artifacts. Those are entire galaxies being bent around the gravitational field of the cluster. Galaxies that would otherwise be too faint and too far away for even Webb to detect are being effectively magnified by the universe itself, brought into view by physics. Webb is using the universe as its own telescope. The universe is helping us see the universe. Second, the distance involved. Some of the objects in that image are showing us light that left its source over 13 billion years ago. The universe is approximately 13.8 billion years old. We are seeing light that began its journey when the universe was less than 1 billion years old. When it departed, Earth did not exist. Our sun did not exist. The atoms that make up your body had not yet been forged in the cores of stars because those stars had not yet lived and died. We are looking at the universe in a state so early, so raw, so fundamentally different from what exists now, that the word ancient does not even begin to cover it. Third, and this is the detail that quietly unsettled a number of cosmologists when they first analyzed the image, some of those galaxies look wrong. Not wrong as in damaged or distorted, wrong as in they should not look the way they look at that age. They appear too developed, too structured, too massive for objects that should be only a few 100 million years old. We will come back to this, because it matters enormously. It might be the most important scientific problem Webb has yet surfaced. The dying star that rewrote what we know about death. Let us talk about the Southern Ring Nebula, because this is the image that, in my opinion, deserves more attention than it typically gets in discussions of Webb's early releases. A planetary nebula, despite the confusing name, has nothing to do with planets. The term comes from the 1700s when early astronomers observed these round, glowing objects through primitive telescopes and thought they resembled planets. They do not. What they actually are is the final exhale of a dying star. When a star like our Sun, a medium-sized star, reaches the end of its life, it expands into a red giant, sheds its outer layers in successive waves, and the core left behind becomes a white dwarf, a dense, hot remnant about the size of Earth but with a mass close to that of the Sun. The ejected material glows from the radiation of that dying core, creating the beautiful shell structures we call planetary nebulae. The Southern Ring Nebula, designated NGC 3132, is located approximately 2,000 light-years away. It had been photographed before. Hubble had captured it. We thought we understood it. Webb photographed it in 2 different wavelengths of infrared light simultaneously, and what the longer wavelength image revealed stopped the analysis team cold. There was a second star. Inside the nebula, at the center of the dying system, there are 2 stars orbiting each other. One of them is the white dwarf responsible for creating the nebula, the one that died. But in Webb's longer wavelength image, the white dwarf appears surrounded by a dusty ring that the companion star, still alive and still burning, does not have. Here is why that matters. The dust around the dead star means that during its final stages, as it was shedding its outer layers, it was interacting with its companion. The companion star, orbiting through those ejected shells of gas, gathered some of the material around itself and then released it again, shaping the nebula's structure. The rings and arcs and complex nested shells visible in Webb's image are not the product of one dying star alone. They are the product of a binary system, 2 stars dancing together in death, each influencing what the other's end looks like. We did not know this from Hubble. We could not have known this from Hubble. Webb revealed it in a single observation. The implication for our own solar system is something most science communicators politely sidestep, so let me just say it directly. Our Sun is a single star. It will become a red giant in approximately 5 billion years. It will shed its outer layers. It will create a planetary nebula of its own. And because it has no companion star to complicate the process, its death will be simpler, more symmetrical. Earth will be incinerated during the red giant phase long before the nebula forms. This is not a comforting timeline exactly, but 5 billion years is a very long time, and I am choosing to not lose sleep over it. What I find genuinely moving about the Southern Ring Nebula image is something more philosophical. That dust ring around the dead star, the material it shed, the complex chemistry being driven by the radiation of the white dwarf. That dust contains carbon, oxygen, nitrogen, complex organic molecules. It is the same kind of material from which planets form, from which life eventually emerges. Every dying star is simultaneously an ending and a seeding of the next generation of chemistry. The universe recycles itself in the most extravagant way possible. The exoplanet revelation. We can now read the atmosphere of worlds. We cannot see. Here is where things get genuinely unsettling in the best possible way. WASP 96b is an exoplanet, a planet orbiting a star other than our Sun. It is located approximately 1,150 light-years from Earth. It is a hot gas giant, roughly half the mass of Jupiter, orbiting its parent star so closely that a full year on WASP 96b lasts only 3.5 Earth days. The surface temperature is estimated at around 530 degrees Celsius. It is not, by any reasonable definition, a pleasant place. Nobody is suggesting WASP 96b is habitable. That is not the point. The point is what Webb did when it observed this planet. Instead of imaging WASP 96b directly, which is essentially impossible because the light from its parent star overwhelms any light from the planet itself, Webb watched the star for 6.4 hours as the planet transited or passed in front of it. As the planet moved across the face of the star, starlight filtered through the planet's atmosphere. Different molecules in that atmosphere absorb different specific wavelengths of light. By measuring precisely which wavelengths were dimmed as the planet transited, Webb could construct a chemical fingerprint of the atmosphere. This technique is called transmission spectroscopy. It has been used before. What Webb did with it had never been done before. In a single observation, Webb detected unambiguous evidence of water vapor in the atmosphere of WASP 96b. It also detected signs of clouds and haze, far more complex cloud structures than previous observations had suggested. And in subsequent observations using this same technique on another exoplanet, Webb became the first telescope to definitively detect carbon dioxide in the atmosphere of a world outside our solar system. Read that sentence again if you need to. We detected carbon dioxide in the atmosphere of a planet 1,000 light years away, a planet we cannot see directly, using the shadow it casts across a distant star. The reason this is not just scientifically impressive, but philosophically staggering, is what it implies for the search for life beyond Earth. Because the molecules you would look for in the atmosphere of a potentially inhabited world, oxygen, methane, water vapor, carbon dioxide, exactly the kind of biosignature molecules that life as we know it produces and depends on, these are now detectable. Not theoretically, not eventually. Now, with Webb. Today. Webb does not have the resolution to do this for an Earth-sized planet in a habitable zone orbit around a sun-like star. Not yet. That is the honest caveat that needs to be stated. The planets it can currently characterize atmospherically are large and close to their stars, because that makes the transit signal easier to detect. But the technology exists, the method works, the data is real and clean and unambiguous. There are scientists right now who are extremely quietly, very carefully, not getting their hopes up, pointing Webb at smaller, cooler planets orbiting smaller, cooler stars, where liquid water might exist on the surface, and waiting to see what the atmosphere looks like. Nobody is saying anything publicly yet, but they are looking. What Webb is about to show us next, and why it terrifies some scientists. Let me tell you about a problem that has been quietly growing in cosmology for the past 2 years, because Webb is directly responsible for it, and it does not get nearly enough attention. The standard model of cosmology, the lambda CDM model, if you want the technical name, predicts with considerable specificity how the early universe should look. Right after the Big Bang, roughly 13.8 billion years ago, the universe was hot, dense, and almost perfectly uniform. Small quantum fluctuations in that primordial soup eventually grew, under the influence of dark matter, into the first structures, clouds of gas that eventually collapsed into the first stars and galaxies. This process takes time. The models are quite specific about this. The earliest galaxies should be small, irregular, still assembling themselves, chaotic, young. Webb started looking at those earliest galaxies. They are not small. Multiple teams of astronomers, analyzing Webb's deep field images and subsequent targeted observations, have identified galaxies in the very early universe, some of them existing when the universe was only 300 to 500 million years old, that are far more massive, far more structured, and far more chemically evolved than the standard model predicts they should be. In 2023, one team published findings describing what they called impossibly early galaxies, objects so massive and so well formed at such an early cosmic age that they presented a genuine challenge to our understanding of how structure forms in the universe. One of these galaxies appeared to be roughly as massive as the Milky Way, but existing when the universe was only 3% of its current age. Under current models, there simply had not been enough time for that much mass to assemble in one place. Now, it is important to be precise here, precise and honest. This does not necessarily mean the Big Bang did not happen. The evidence for the Big Bang is overwhelming and comes from dozens of independent lines of observation entirely unrelated to what Webb is seeing. Nobody serious is suggesting we throw out cosmology and start over. What it might mean is that the process by which galaxies form in the early universe is not fully understood. That dark matter behaves differently in some contexts than current models predict. That star formation in the early universe was faster and more efficient than we thought. Or possibly that some of our distance estimates for these very early objects, which are derived indirectly through a measurement called redshift, contain systematic errors that need to be corrected. Any one of these explanations, if confirmed, would be a significant revision of our current understanding, not a revolution. A revision, but a meaningful one. The fact that Webb keeps finding these objects, keeps turning up galaxies that seem too big too soon, is a pattern. And patterns in scientific data are not things you explain away. They are things you investigate. Webb's upcoming observation programs include deep surveys of multiple sky fields specifically designed to find more of these anomalous early galaxies, map their distribution, measure their properties, and determine whether they represent a genuine challenge to current models or an observational artifact. Some cosmologists are very eager to see these results. Some cosmologists are rather hoping the problem quietly resolves itself. It probably will not quietly resolve itself. The truth nobody wants to say out loud. Here is the uncomfortable thing that sits underneath all of this. The standard model of cosmology, the one we have spent decades building, testing, refining, teaching to students, publishing papers about, was constructed without the benefit of data from the very early universe. We had theoretical predictions. We had indirect evidence. We had the cosmic microwave background radiation, the afterglow of the Big Bang itself, which is extraordinarily well measured and extraordinarily well understood. But we had never actually seen the early universe in detail. Not really, not like this. Webb is showing us the early universe in detail for the first time. And in multiple respects, it does not look quite the way we expected. This is not a scandal. This is not a conspiracy. This is science working exactly as it is supposed to work. You build the best model you can with the available data. Then you get better data, and you update the model. But there is something psychologically significant about the scale of potential revision here. When the data being returned by a single telescope is sufficient to prompt serious peer-reviewed papers questioning whether galaxy formation in the early universe proceeded the way our best models predict, you are not talking about tweaking the numbers. You are talking about potentially rethinking some of the assumptions that underlie the structure of modern cosmology. That is not terrifying. That is extraordinary. That is exactly the situation you want to be in as a scientist. Standing at the edge of what you know, looking at data that does not quite fit, knowing that whatever explains the discrepancy will be more interesting, more true, and more beautiful than the explanation you had before. That is what the James Webb Space Telescope has given us. Not answers, better questions. Somewhere in the Carina Nebula, 7,600 light years from this planet, a star is being born right now. Its jets of material are blasting outward through the dust. Its gravity is pulling together the raw material of what might become planets. Chemistry is happening in the disk of gas and rock surrounding it that given billions of years and the right conditions, could eventually produce something that looks up at the sky and wonders what is out there. We will never know about that particular star. By the time its light reaches us, everyone reading this sentence will be long gone, along with everyone they ever knew. But Webb showed us the same process, happening in the same region of the same nebula, in an image that looked like something dreamed up by a poet who also happened to have a doctorate in astrophysics. Here is the thing I keep coming back to, the thing I think gets lost in all the technical discussion about mirror sizes and infrared wavelengths and gravitational lensing. We are a species that, not very long ago in cosmic terms, was huddled around fires on a small planet, looking up at lights in the sky and making up stories about them because we had no idea what they were. And now we have built a machine that sits 1.5 million kilometers from home, in the coldest shadow it can find, looking back at the first light that ever existed, seeing galaxies being born before our sun had formed, reading the chemistry of atmospheres around worlds we will never visit, and asking carefully, scientifically, honestly, whether anything out there is asking the same questions we are. James Webb did not give us the universe. It gave us our first real look at it, and what we saw was stranger, larger, older, and more beautiful than we had any right to hope. We are just getting started.